So hello everyone, this is lecture 7 for the electricity and magnetism. In the last lecture we were discussing about the electrostatic energy, and today we will moving forward to the Poisson's and the Laplace equation. So what are these equations? So you already know the differential form of Gauss law, that is del dot E equal to rho by epsilon, and we know that E can be written as minus gradient of V, that is potential V. So if you substitute this value of E inside this, you will get del dot minus del V equal to rho by epsilon. From here it will become del square V equal to minus rho by epsilon. Now this equation is called the Poisson's equation, and if in some particular reason we have found that charge density is 0, then del square V will become 0, and this is called the Laplace equation. Now these are the results. Let's see how can we use them. So there are many questions based on this. So let's see the one question. In a coaxial cable, coaxial means there is same axis and you have this type of structure, circular, spherical. The radius of the inner conductor, these are two conductors. The inner conductor radius is 2 mm and that of the outer one is 5 mm. The inner conductor is at the potential 10 volt here, while the outer conductor is grounded. Find the value of potential at R equal to 3.5 mm from its axis. So we need to find the potential at this point. So let's see how can we find this using the Poisson's equation. So see, inside this the charge density is 0, that's why we'll use the Laplace equation. Del square V should be 0. Now del square V equal to 0 we already seen in the vector analysis in the mathematical physics. So that del square, how can we write del square as 1 upon R del by del R del V by del R equal to 0. Now from here R will become 0, so del by del R del V by del R equal to 0, and from here you can solve this, means this equal to 0 means this should be some constant. So R del V by del R should be some constant A. From here we can use the separation of variable. Take del R with R and A here and del V. So 1 del V will give you V, and 1 upon A upon R del R will give you A log R plus B. B is some other constant. Now some initial conditions are given, that at the R equal to 2 mm it is 10 volt. So V is equal to 10. At R equal to 2, so it will be A log 2 plus B, so we get one equation. Now at the R equal to 5 we get the potential 0 because this is grounded. So 0 equal to A log 5 plus B. You have two these equations and variable is only 2, A and B, so you can find the value of A and B very easily. A will be this and B will be this. Now you need to find the V at 3.5, so you have this equation, substitute A and B here, and V at R equal to 3.5, you can just calculate V 3.5 from direct this equation. So that's how you can use the Laplace equation here. So let's see one more important case. You must remember this. So if potential is given in this form, A exponential minus lambda divided by R, we need to find these three things: electric field, charge density, and the total charge in the whole space in the spherical symmetry. It is given in the spherical symmetry, then we need to calculate. Then we know what is E. E is minus del V, gradient of V, and V is given, so we need to just find the gradient of this. In the spherical symmetry it is del by del R V and R cap. So del by del R of V is this, so we need to find the differentiation and partial differentiation with respect to R. So V is this, so we will take it is as two function, 1 upon R multiplied by exponential minus lambda R. Use the product rule, we'll get this, and E will be A1 plus lambda R exponential minus lambda R cap divided by R square. So this will give you this. Now you have electric field. Now using the Gauss law differential form, you can find the charge density, that is epsilon naught del dot E. So del dot E and E is, you already find it this, so it will be epsilon naught and A. Now you will just multiply del with E, and E is this complete value, so it will be 1 plus lambda exponential minus lambda del dot, means here you will use product rule again. You will just separate these two functions, means you will take this as first and this is as second. So first you will take with the R cap by R square, take this as constant, then plus this will be with this gradient with this, and this will be outside. So we have just used the product rule here in the del dot E. Now see, what is this? We already discussed this in the vector analysis, that this is the Dirac delta function, and this 3 just represents the volume integral. So means this is 3, 2, 1, this all are same, this is just the representation. So it will be 4 pi Dirac delta function R. So it will also exist only for R0. This is 3's because we have 3 variables here, x, y, z. That's why we are using 3 here. So this is Dirac delta R plus epsilon naught A R by R square, and again you can find the differentiation of this. using the product rule. First it will be means you can take one function and the second, so it will be this, means I have calculated this term proper here, epsilon naught a divided by r square. Then you just solve this for here. First we take this as constant, find the differentiation of this, then take this as constant, and the differentiation of this will give you this. Now you can solve this. One term will cancel out, e minus lambda r lambda will cancel out with minus lambda s minus lambda r. You will get one term remaining, that is lambda square. So this will be coming out of this. This is solved as this. Now we just see this. This will be can be written in this form. This is the same thing we have written, and this will solve to this. So charge density will be this. So you have the answer for the charge density at any point r, at any vector r. Now the third is we need to find the total charge in the whole space. So you know how to find this. We know charge density. So rho d tau will give you charge in the complete space. So this is a volume integral. So in place of rho, just substitute this value, complete value. So we get this. Now this is a two different things. So we'll just take the integral of this and integral of this. Now for the integral of this first term, you will see this is a Dirac delta function is involved here. So this will exist for r equal to 0 only. So we'll put r equal to 0 here and 0 here. So you will get epsilon naught a, and it will be 1 here, and it is 4 pi. So you will get 4 pi epsilon naught a only. So this is the property of Dirac delta function. Now you can solve this integral very easily. This will cancel out, this will give you r. So r exponential minus lambda r integral, use the integration by parts. So you will get this value 4 pi epsilon naught a, and the net charge will be 0. So in this case, total charge in the whole space will be 0. So see, we are getting some charge density, but net charge is 0. So because charge density can be somewhere negative, somewhere positive, and that's how you can get the total charge 0. It doesn't need to be true that if total charge is 0, that density must be 0. Okay. So that is the case. Let's start the new topic today. That is properties of conductors. Now see, we will discuss two type of things, that is dielectrics and the conductors. So what is the difference between them? Dielectrics are the some atoms which is very tightly attached with each other, and means the electrons will be tightly attached. Electrons are not free to move inside a dielectric, but in the conductors they are free to move very easily. For each atom you will have 2 to 3 electrons which are free to move. So that is the difference between dielectric and the conductor. So what is the electric field inside conductor is 0. So electric field inside a conductor will always be 0. Why? We have some conductor and there is some electric field. Then you will see that electrons which is free to move, they will move with the electric field. If this is in this direction, electron will move in this direction and make the negative here and the positive here, and it will make a net electric field in this direction. So this electric field will keep increasing until this becomes equal to the outside field, so that net electric field inside the conductor will always be 0. So in the conductor they will increase the electric field, electrons will continue to move until the net electric field inside the conductor is 0. So this is equal to 0. Now see, if total charge means electric field is 0 inside, then charge density must be 0 inside. So if electric field is 0, charge density inside conductor is always 0. Now if charge density is 0, electric field is 0, then potential will remain constant throughout the conductor. So there is no need to no work is required to move from one point to another point inside a conductor. So inside conductor potential is constant, because potential is given by E to dl, A to B. To move A to B, this potential is given. Now E is 0, so this will be 0, means VB equal to VA. Potential at B and at any point B will be equal to at any point A. So the potential will be same in whole conductor. Now there is no net charge inside the conductor. If there is some charge is given to the conductor, extra charge, net charge, then that will lie on the surface only. Means it will net charge inside the conductor will always be 0. That's why any net charge will be lying outside the conductor. So any net charge reside on the surface only. And if you have a unsymmetrical structure of the conductor, then charge means the electric field at the net charge will lie outside the conductor on the surface, and electric field will be perpendicular to it always. So at any point will be perpendicular, and charge is also unsymmetrically distributed. Where you have the lower area, there will be large charge, and when the large area, charge will be more widely distributed. So you can see that charge density at A point is large as compared to charge density at B, because it's unsymmetrically distributed. So charge will also be unsymmetrically distributed. So this is a property of conductor, and inside will always remain 0. Charge density 0, electric field 0, and V is constant inside the conductor. Now see, electric field cannot penetrate the conductor also. If you have means you have some conductor, and Means first this thing, electric field cannot penetrate the conductor. We already seen this thing, that if you have the electric field, net field inside is 0, that's why it is not penetrating. So if you have some conductor unsymmetrically distributed and you have inside some cavity and there is no charge here, just let's assume there is no charge here, then electric field inside this cavity will be 0 because using the Gauss law. But let's say if we have some charge inside, plus q, then there will be inside and some electric field in this cavity using Gauss law. But itself means if it is charge here, now also there will be no electric field inside this conductor. Why? Because if there is plus q charge, there will be electric field setup that will come make this negative charge come to this surface because of this direction of the electric field. Now this negative charge, and that's how it will create a plus charge here, and this negative charge will be equal to minus q because here is plus q. So this again, if you take the Gaussian surface here, so net charge inside will be 0 and electric field will become again 0. So the charge will move that way that total electric field, net electric field will always be 0 inside this, and net charge density will be 0. So if you place plus q charge here, then it will bring minus q charge here and plus q on the surface, and now also the total electric field is 0 here. And if you have some plus q charge outside, then this electric field cannot penetrate this conductor, and it won't affect anything because it is again have the same property like this, and net electric field will be 0. So if you have some outside charge, then there will be no force due to this charge at this charge because electric field can't penetrate this conductor. But there can be a net force at this charge because of this conductor, because you will see that plus q charge is coming over the surface. So that can give some force, and you have to take the superposition of all these charges to find the electric field at this point due to this conductor, not because of this plus q charge, because there is no electric field penetrating through this surface. Okay, and there will be no force because of plus q charge, so there is no interaction between plus q and this q charge. So you must remember this. That's why we can say that electric field cannot penetrate the conductor. And there is one more property, that if you have any conductor and there is some plus q charge outside, so it can be plus q or minus q, it will always be attracted towards the conductor, because for the plus q it will be make a negative in the conductor, and plus here it will be attracted again. If it is minus q, it will make plus here, and the minus here it will be again attracted. So for any conductor, if you have any charge, it will always be attracted towards that conductor. So that's how you can see that force will be applied by the conductor, not the inside charge. So because there is no interaction between these two charges because of no penetration of electric field. So that's all for today. In the next lecture, we'll discuss some more properties and some questions. Thank you everyone.